The second thing you need to understand these solar radiation modification techniques is the structure of the atmosphere. Just think about air. Imagine you have a cube of air sitting here. If it's a 1 cubic meter for air, it weighs about 1 kilogram, which might be the same as a water bottle. If I drop the water bottle, it falls. I mean, the kilogram weight falls. It would hurt me when it lands on the ground. Why doesn't a cube of air fall as well? Well, the reason is that there has to be a pressure gradient. So there's atmospheric pressure on the bottom and atmospheric pressure on the top, and the pressure on the bottom must be bigger than the pressure on the top, and that difference balances the weight of the air and keeps it up, so the air in this room doesn't all fall to the ground. Okay, so atmospheric pressure goes down as you go up to higher altitudes. What about temperature? Well, let's imagine we take this block of air and we move it upwards. Now, if it's a big enough block of air and it's moving fast enough, then not much energy is going to come in or out. There just isn't time, and air is a pretty good insulator. So this is what's called adiabatic motion. Adiabatic is like Latin for nothing going in or out. So no heat goes in or out. So as this blob goes up, no heat energy is exchanged with the air around it, or no significant amount, but it's still in a region with lower pressure, which means that it will expand. As it expands, it's doing work on the surrounding air, so that it needs energy, and that energy has to come from its internal heat. So this is a long way of saying that when you take air upwards, it expands and cools down. And this turns out to be, it'll drop in temperature by about 9.8 degrees centigrade for every kilometre you raise a parcel of air. And this is called the dry adiabatic lapse rate. Lapse rate means the rate at which it goes down as you go to higher altitude, and this is dry because this is just dry air without too much more moisture in. Adiabatic because no energy is assumed to be coming in or out. So you have a graph here with altitude and temperature, and if you had some gas at this temperature at low altitude and you push it up, its temperature will drop as it goes up. Okay, so that's dry air. Wet air does something different. So let's imagine now we take a parcel of air which has water vapour in it, like most air on Earth does at some level, and you push that up, and as it goes up, to begin with, it just cools down and expands just like the dry air. But eventually, at some point, it will get so cold that the water vapour will start to condense out, creating droplets of water, solid water, liquid water, inside this mass of air. This is called the saturation point. It's the point at which the temperature has dropped enough that the water is saturated, and you'll start getting the water vapour condensing out. So as it moves up here, it will reach the saturation point. Now at that point, if it continues to rise, things happen a bit differently. Now, it's continuing to rise, so it's continuing to get colder, but now more and more water vapour is condensing out. And water has a large amount of latent heat, 2 million joules per kilogram, and as it turns into liquid, that heats the air up. So what happens is it does continue to cool down, but now it cools down much less because as it's releasing more and more latent heat as this water condenses out. So the temperature only drops now by about 5 degrees C per kilometre. It depends on the exact humidity and temperature. It can be between 2 and about 7. But anyway, much less than it did before. Now this is why clouds often have clear bases. What's happening is you've got air that's rising, and to begin with, it's rising at the dry rate. But then, when it reaches the bottom of the cloud, that's when it's hit the saturation point. And now as it continues to rise, water droplets come out of it, which is what causes the cloud. The cloud is just tiny micron-sized water droplets. And that gives you this characteristic flat bottoms of many clouds at just the right altitude where the air moving upwards by convection starts to become saturated. How does the water vapour come out of the gas and form droplets? Well, normally it does this by condensing around tiny solid particles. If you take totally pure air with no particles at all, you can actually cool it well past the saturation point and nothing will form. But luckily or unluckily, there is always some dirt and dust and small particles in the atmosphere, and these act as nucleation points, and the water droplet condenses around them. These tiny particles might be dust blown up from like the Sahara Desert. It can be ammonium sulfate from plankton, that's actually what dominates over the oceans, or in fact human pollution. So that's like these orange bits in the middle here, and the water droplets form around them. And as time goes on, the water droplets get bigger and bigger as more water vapor condenses around these particles. If enough water condenses so the particles get quite big, like tens or hundreds of microns, or even up to millimeter size, that means that now, thanks to the square cube law, their gravity can start overcoming the drag and they'll fall out of the cloud. And this is known as rain. So the idea would be that the air rises, then it starts maybe rising a bit faster inside because of the extra latent heat, and the droplets form as these tiny fog-like droplets merge and more water vapor condenses on them until it gets heavy enough to fall out.